this presentation is about Kafka. Who has heard of Kafka? Who has not yet found a use case for Kafka? Yeah, same problem. Okay, who's using it already? Nice, 1, 2, okay, a few people. It's always the same with new technologies that, you know, the Gartner curve or whatever it is, where you have adoption first by a few early people, they iron out the rough edges, and then follows the hype, and then the reality. And I think Kafka is now probably at the tip of the hype curve, where everybody's using it. I'll show you one slide with a lot of bullet points later. And it's now stable enough, I think, and has enough really good features that make them worthwhile. And if you've read my abstract, you will have noticed that I talked about information interchange in a way, and how it can also serve to just change the way we build distributed applications, especially in a microserviced world, especially with functions as a service, which is a better term for serverless, which is a stupid term, I think. So that's what Kafka can be used to. And it can guarantee, it doesn't have to, it's up to you, whether or not the message actually goes through to your code. My name is David. I work for Heroku. And at Heroku, we both offer Kafka, and we use it internally. So we used to, as you can imagine, if you run a platform as a service, there's a lot of moving parts, a lot of events that need to be shuffled through somewhere. And we initially adopted Kafka internally and then realized this is a pretty good product. So it was a win-win situation to build a team around it. If you have questions, you can ask me via email or via Twitter. I cannot respond for the next couple of minutes, so if you want to say bad things about me, I cannot defend myself. Kafka is named after Franz Kafka for no particular reason. The guy who invented it just read a Kafka book when he started working on it. It's actually an Apache project, which is not always a good sign, right? But in this case, I encourage you to check out the website, because unlike, has anybody ever used Flume? Apache Flume, for instance, a similar-ish on the surface project. And that, like many Apache projects, doesn't have a very nice website, and it's not a website that looks like it's been updated since the late 90s, right? But Kafka actually has a really nice website, which is the first promising sign that it might be something really good. And then you start Googling around, like, what is it? What can I use it for? And then somebody tells you, well, it's basically a massively scalable pub/sub message queue architected as a distributed transaction log. So you think, oh, it's a queue. But it is not a queue. It can be used as a queue, but in particular, it's not very good at the typical queue things like retries that are built into the queue manager, or stuff like, you know, with a queue system like Beanstalk, you can say, run this task in 8 minutes, or run this task tomorrow at midnight, which is really nice if you, for instance, have a sign-up in your system from a new user, and then onto your Beanstalk task queue, you put a job to say, tomorrow at midnight, you'd send him the welcome to our system, here is the first steps, welcome email, right? So Kafka is not really good for that. One of the reason is it's not designed to be purely a queue. It can be used as that. A pure queue has the problem that it cannot have multiple subscribers, right? So if one process consumes messages from a queue, the messages are gone. That's why it's a queue, right? So you cannot hook up an arbitrary number of consumers to a queue, which in a message-based architecture is not useful, right? Because you just want to make a stream of messages available, and then anybody can hook up to this stream of messages and do something useful with the information. Okay, but there was something about pub/sub, so it's a pub/sub thing, right? But it is not a pub/sub thing. Because pub/sub has the problem that it broadcasts messages to all subscribers. And if you have a lot of subscribers, that means a lot of I/O and a lot of unnecessary messaging. You want consumers to be able to hook up to just the information they are interested in. So it's a log. It's not something like a captain's log. It's more like a wall. Who knows what that stands for? Okay, Postgres users? Any? Have heard of a tool named Wally maybe before, just with one L? Eva. It's a write-ahead log, okay? So write-ahead logs are really, really, really great. And they are used by a number of systems in the world and have been for a long time. It's an old architectural pattern for databases. CouchDB, for instance, uses it, right? So fundamentally, you say, well, you have a message and another message and another message and another message, and you only ever append to it. In CouchDB specifically, that means you create a document, and that's recorded in, you can almost think of it as a text file, right? It says document number 1 was created, and then maybe it was updated, and then another document got created, and then another document got deleted, right? And Postgres internally works the same way. So Postgres, when rows are added to a table, when you delete records, etc., it appends that to this write-ahead log. That's really useful because you can stream the write-ahead log directly to file. You can just take the write-ahead log off the file system and you have a backup of your database. You can then compact it because there's a lot of useless information, right? If you update the row 5 times, you can remove 4 entries from the write-ahead log to compact it. So this is periodic database maintenance you can do. You can also use this log to replicate information to another server. But the best feature about a write-ahead log is that it's absolutely never possible to corrupt it, because any operation is append only, right? So if you, like an old database format like MyISAM and MySQL does in-place edits. And that's bad because if you're writing to a particular point in the database and I pull the plug from the server at just the wrong moment, right? And the power's out and it doesn't have a backup power supply, etc., then the database might be corrupted. With a write-ahead log, because everything's append only, I scan to the end of the file, read back a few bytes to the last terminating header, and I can resume, right? I might lose some data, but losing data happens when you pull the power plug from a server, so that's inevitable. The other benefit of a write-ahead log is that I/O is always sequential, because you don't have random disk seeks. You just stream information to a disk or an SSD. Disks are particularly happy about this, but SSDs also benefit, right? I mean, SSDs have orders of magnitude better random performance than traditional hard drives, but even SSDs perform better when you write or read sequentially. And the sequentially is key, right? So Kafka assumes that everything in the system will be read at least once, because why would you otherwise record it, right? So it only ever appends things, assuming that you will also read sequentially, because that's the guarantee it makes. It says the order in which information comes into the system is also the order in which information goes out of the system. So internally, Kafka uses crazy optimizations, and it's written in Java and Scala. So it uses like JVM primitives like the transfer to file channel, which, depending on the implementation in the operating system will actually take a chunk of bytes from the disk cache and move it straight to the network interface. And it never hits the RAM, right? It's like it doesn't get copied around in memory. And these couple of architectural constraints that they explicitly chose are the reason why Kafka is really, really quick, right? So on a regular, this is a standard Apple Keynote placeholder image, but I thought it was a really good example of something that's fast. And if I were interested in dying in a motorcycle accident, that's the motorcycle I would ride, I think. So, because I don't think I would be a good motorcyclist. Anyway, so on a single cheap server, even on this laptop, I can probably get 100,000 messages per second, right? On a cluster, achieving millions, billions, even trillions of messages a second is absolutely not a problem, right? Due to its distributed nature. How you exactly achieve that, we will talk about in a moment. But the key is the sequential nature of the system. Because when you write data sequentially, and it just gets flushed to disk from the cache periodically, etc., then it no longer matters whether you write 1 megabyte messages or 50 kilobyte messages or 300 byte messages, right? Because you always write something in the chunks of a couple of megabytes off to disk. So it's always fast, no matter what the message size is. The throughput, the effective throughput through the system, of course, changes with message size, right? Because then at some point you also have network I/O to consider, and a lot of small messages have a bit more overhead than fewer smaller messages. But fundamentally, its internals don't care, which is nice. So you organize messages in Kafka in so-called topics. You cannot have arbitrary number of topics. So you don't want millions of topics. Managing topics to Kafka is expensive, right? Deleting it, etc. It needs to do maintenance internally. So you wouldn't have a topic per customer. You would have a topic called customer activity or something, right? And in there, you put website activity on your online shop or whatever from all customers. And then how you figure out what customer record belongs to what, I'll show you in a moment. But fundamentally, topics are streams of messages, right? Or streams of records. So first, second, third, and internally, actually, in Kafka, they have a so-called offset, right? So they start on 0, probably. Sorry. 1, 2, 3. Imagine there was a 0. And then that keeps going on and on and on, right? So the data grows only ever sequentially. And you can then hand that off to stuff that consumes it in the same fashion. Because the producer of data writes always to the end of the list, and then you can hook up a consumer or many consumers to that stream. And yeah, many consumers. To get scale into the system, you can use so-called partitions. So instead of just one, you have multiple rows within the same topic of columns, if you want to imagine it like this, right? So they all hold a fraction of the information. If you don't do a specific assignment to a topic, it'll often be done randomly, right? So your messages go in somewhere. And now the key is that you can have a so-called group of consumers, and then one consumer reads this partition, another reads this partition, another reads this partition, another reads this partition. And they all extract user information, for instance, from the website click stream, right? And then you have another group of consumers that you hook up to this topic, and they maybe have code that's written to detect attacks or abuse or login attempts that fail too often or something like this. So this gives you scale because, for two reasons. The first I already said, you can hook up a consumer to each partition, right? And the second reason is you can then scale out on machines. So each partition can live on a machine. In Kafka, you store messages, topics, and in partitions, and the partitions always live on individual producer, on instances in the cluster, right? And they have disks, so you can store a terabyte of log streams on an individual server, but eventually you can't add more hard drives, right? So partitions are a way of scaling the amount of data as well. Each partition will then live on its own server. And the parallelism we already talked about. And in multi-consumer, multi-topic, multi-partition setups, it looks roughly like this. It's a blurry picture taken from the website because I don't have the drawing skills to produce this. But you then have the different partitions, and everything basically can go to everything if you wanted to, right? So this consumer group has 4 processes processing a chunk of the topics, and here you see that multiple partitions data goes to one consumer. So if we produce information, that always needs to be, well, fundamentally a byte array, right? So it can be a file like a JPEG image, but why would you do that? It's typically either plain text. So one common thing could be just log lines from Nginx or Apache, right? And then you parse them in a consumer, for instance, and pass them on somewhere else. Or it's JSON, or it's a more structured format like Thrift or Avro, for which you can then generate code on clients to use it. Sorry. So, and the key about the producers is, we talked about the partitions earlier, right? So how do you know which message goes into which partition? Because that's where the secrets come from. If it's just random, you might not be able to do something interesting with the data. So imagine these were clicks by users and the information contained the user ID. What you could then do is you could say, oh, if all the same users always end up in the same partitions, right? So users 1, 2, 3 go here, users 4, 5, 6 go here, and so forth. Then you can have code that in a loop sees, oh, he's logging in and emits an event somewhere else. He's now logging out and emits an event somewhere else, right? The consumer in a loop reads messages and remembers information in memory if you wanted to, for instance. So you can do aggregations and stuff. So you either explicitly choose a partition, but that's not very useful because then your code knows how many partitions there are and has to have logic how to split it, or you just assign the message a key. So for user activity, the key for a message would usually be the user ID. And then Kafka, based on the ID, and because it knows how many topic partitions there are, based on the ID you give it, decides, okay, this ID always consistently goes to that same partition. And then you can do aggregations, for instance, right? So you can sum up the number of clicks from a user within a period of time or something like this. And you can even retroactively do this. So whatever a producer writes, any byte array, anything, unlike in a queue where when you read it, it's gone, it's persisted to disk, right? So you can say Kafka should store every message that goes into the system for 2 weeks or for 24 hours. You could say it should start discarding old messages when it reaches a certain size limit. And then in the consumers, they just get fed the information based on the key. They automatically get distributed across the number of partitions, etc. So you don't have to really worry about it. You just say, I have a name like this. I'll show you the code example in a moment. But the key about consumers, unlike topics, which incur a lot of maintenance overhead on the cluster, is that consumers are cheap. Because it's really just a network connection, and the consumer, when it connects to the Kafka cluster, says, my ID is such and such, and then it starts receiving messages. And the only information the consumer sends back is the offset. So a consumer says, I have read until message offset 785,433, right? And then the next time it hooks up, the Kafka cluster will resume at that position if it crashes, if it has to restart for whatever reason. But because, remember, everything's always retained, you can write new code and say, because we're remembering everything in the cluster for 2 weeks, for instance, right? I can write new code that now for the data for the last 2 weeks just does some processing. And eventually, then you can scale that up with a lot of processes. And when you've catched up with 2 weeks worth of data, you start scaling down, and then you're always, your code can deal with the older information. And this is nice because it means you can have millions of, well, not millions, but you can have hundreds of thousands of consumers, and the cluster doesn't really care, right? And like I said earlier, the cluster guarantees you that the messages are in the right order. So a lot of event information you feed into such a system is time-based, right? So naturally, you emit an event, a message, and then another, and then another, and then another. And you are guaranteed that your consumer code will always get it in that order within a partition. So if you have 2 consumers, for instance, for 2 partitions because you want parallelism for your user events, let's say all odd user IDs go to this one, all even go to this one, and it'll be always in the right sequence where the events happen in real life. And consumers, when you do something with a message, you can again produce information, output, right? So you can build complex flows saying, okay, my first consumers parse an Apache log, produce another event. And then I have more consumers that hook up to these produced events. And then over time, you filter information down, or you write information to S3 to back it up. You write information to an SQL database, right? Stuff like this. And you can build a series of tubes. So in PHP, you use RD Kafka, the RD Kafka extension. So librd Kafka is written by a Swedish person. That's what exposes bindings to many languages. And Arnaud Leblanc has written an extension for PHP. It's pretty feature complete. It no longer really crashes all the time, so it's pretty decent. And then you can write code that does something with information, right? So if you say, well, I'm interested in everything, but it doesn't have to be guaranteed that I never miss a message, right? You say, you set up a little bit of a confirmation, you say connect to this broker or something like this, and then in a loop, you get a message, and you do something with it, and then you're done. Now, that is called at most once delivery. Meaning, this consumer will never see the same message twice. The reason for that is that it automatically commits information. So if you, well, actually it doesn't have a guarantee about most ones. But if it crashes somewhere in between, right, and the cluster hasn't written information, or if the background process automatically commits information about how far along you were, you could lose messages. Whereas if you want something to be delivered at least once, you say, I want to explicitly handle acknowledgement of messages, right? A good example for this is you want to page on an incident. Let's say you want to build a product like PagerDuty. You really don't want to miss events, right? In worst case, you want an SMS to go out to an engineer who's on call twice to say, hey, production server's down. So the way you do that is you do the same setting up, and then you say, I don't want automatic acknowledgement of messages, where the consumer says to the producer how far he is with the offsets. And then you say, in the loop, you do your job first with the message, and when that has succeeded, you commit. Now, the problem is, in between this line and this line, and for those over here, my laser doesn't go that far. It'll probably cause a feedback loop if we ever go in front. But so the second to last and the last line, if the PHP process crashes in between those two, right, then your do something operation has finished. You have probably committed something to your relational database as a result of this operation, but you have not marked the operation as successful. And then the next time this starts, the Kafka consumer will fetch the same record again. So if you want at least once delivery, then obviously this operation somehow needs to be idempotent, right? So if it comes twice, it shouldn't happen twice. So this is a trade-off. You could, of course, also try and do exactly once delivery, but you can't have exactly once delivery. Ultimately, the reason is physics. Because acknowledgement can always be lost. So there's an old thought experiment called the two armies problem, or the Byzantine generals problem. Imagine there's a monster attacking the world, okay? And the only thing that stands between the aliens and oblivion is two armies. So the two generals are on both sides of the monster, 1 and 2, right? So now they can only defeat the monster if they attack at the same time. So they send a messenger with a horse, because I don't know why, and say, let's attack tomorrow at 7 in the morning, okay? And that messenger makes it through to the other army. And that army's general is like, yes, I am ready. Let's do that tomorrow at 0700. He sends a messenger back. But the aliens have lasers, so the messenger dies on the way, right? So what happens now? The general on the right attacks at 7 in the morning, but the other dude's not there because he thinks he never got the message or he doesn't want to attack, he doesn't know why, right? And you can keep adding loops to this, but because you can never know that the last message you sent actually made it to the other side, or that you can never infer from the lack of a message whether the other person doesn't want to or whether the message got lost on the way, you can't coordinate these things. And that's why you can never be sure. I mean, it's probably obvious from the code that I showed, right? Yes, sorry, animations. If it crashes after this line, what can you do? There's nothing. You could keep the database transaction open, but then what if it crashes before, like after you acknowledge the message, before the transaction completes? It's like chicken and egg. You cannot do this. It's impossible, right? So that's what that problem is about. So you always need to design for this. But in most cases, it's really not a problem, right? In worst case, you look into your database. Has the delete already been done? Has the product already been added or something like this? So that's that problem. Now, I guess an interesting thing would be use cases. Because Kafka has a lot of users, right? Every big startup, corporation, whatever. LinkedIn were the first because they invented it. And what they did was they added, they took every event, every click, every activity that happened on the website as people used it, and they fed that into an event stream. And then later, they hooked up machine learning, recommendations, et cetera, to this event stream, because they had a lot of components who all wanted to know what are users doing on the platform, right? And that's this multiplexing nature, that you have massively scalable horizontal streams of events, and then they can go to many different people who are interested in it. And if somebody internally at LinkedIn wants to write new code that also is interested in the user event stream, they don't have to ask anybody for permission or something. You just add a consumer, and it adds network I/O, but that's it. No other load on the system, right? And then they open sourced it years ago, and now Yahoo uses it, and Twitter, and Netflix, and Square, and Spotify, and Pinterest, and Uber, and everybody, right? So you should probably use it too. But the question is, for what? There's always, if all you have is a hammer, every problem looks like a nail. But the classic usage example that you do first, or that you read in all the tutorials, is you take the Twitter fire hose, and then you filter out all the racist hashtags or something, right? Because you don't want to see them. And then you make a little demo out of it, and it looks like this. That's something somebody built at Heroku. So fundamentally, you can do messaging, right? So with the guarantees around delivery you can do, if you have at least once delivery, you could build a chat system where you can have guarantees around that the other person never loses a message while consuming them. You can track user activity. That's what LinkedIn did. And like I said earlier, if you can be sure that all the activity from the user is in the same while loop in your PHP code, then you can do really, really clever things with the activity data, right? So let's say you put a Redis next to it, and every time you see a user log in, you put him into a Redis list. And then when he logs out, you take him off the list or something like this, or for each user, you remember how long has he been on, etc., and then you can do stuff with that information. You can record runtime metrics, so every couple of seconds, take a snapshot of some sort of status in the system and feed that, right? That's how, at Heroku, we now give people, like, for every minute, what's the load on the server, requests per second, CPU usage, RAM, memory usage, right? The Internet of Things, so if you want to build toasters who don't work when the Wi-Fi is down, and they have to send information, right? It's a perfect use case for many, many of the IoT applications, not so much consumer, but industry. If you run a factory and every machine has a sensor, et cetera, that's a lot of information. And you do not want to build a system where when you design it and implement it, you already have to know who will consume all the information later. And that's when Kafka is perfect, right? But there are more interesting, or I think more elegant use cases, because these are the standard ones, right? So a few things that I think you can do that are really cool. and this is something LinkedIn now does, was not the original design, but they do it now, is you can replicate information between a data center. Right? When I earlier said that Postgres has a write-ahead log that you can use to do backups, you can produce data into a topic, and the consumer sits in a different data center and just replays the information. So maybe the producer on the East Coast of the United States, that would be here, right? Yes. Reads data from a database and sends it, and on the West Coast, you write it to a database. You have latency, but you can do it, right? You can, for instance, do billing. That's how we do it now. So every time we start a so-called dyno, a little server container instance, right? We do that first, and afterwards we say, and now we start billing, essentially, right? So we emit the event after we know the server is up. And then just before we take the server down, we say, stop billing, and then take the server down. And the advantage of that is perfectly durable for the customer, right? Because we boot the server first, and then we emit the billing event. If something goes wrong in between, the server is up, but the customer doesn't get charged for something that maybe never happened, right? And then we say, stop billing first, so you no longer pay money, and then the command goes out to stop the server. If that fails, you still have a server up, but it doesn't cost you anymore, right? So this is how you can use the different delivery guarantees and the different methods of acknowledging before or after your operation to achieve different outcomes. And what's also a really cool thing is, so you saw earlier a consumer. In a loop, it talks to the cluster and says, give me a message, give me a message, give me a message, give me a message, right? So that's a pull model. If you don't read anything, Kafka just writes stuff to disk. Like I said earlier, eventually the disk will be full, but you can use partitioning, et cetera, et cetera. So you can use that as kind of a shock absorber. So if you have data flowing through the system and suddenly there is a DDoS attack on you, right? Suddenly you have a lot of user events. Your systems will not crash. Because let's say you have 2 or 3 or 4 or 50 processes consuming your website activity. Now suddenly there's a lot of information, but it just grows longer on the list, right? Because in other systems that did distributed messaging or logging, earlier I mentioned Apache Flume. In Flume, it's a push model. So the server starts pushing more and more and more and more messages onto you, and eventually the listen backlog on the server is full or something because too many connections and stuff crashes, and then you wake up in the middle of the night. But this doesn't page you at 3 a.m. if a script kiddie somewhere runs a DDoS on you, right? So that's I think, a really, really cool thing, and that's what a lot of people use to shovel data from. I mean, let's say you want to write the Twitter stream to a MySQL database, right? You can use that as long as volume is low. You filter out a hashtag for the Super Bowl, for instance, in the United States, right? Like that's always the most hashtag tweets per second. So everything's fine with Super Bowl because it's not yet happening, and then suddenly it's the night of the Super Bowl, and suddenly you're trying to do 500,000 inserts per second. You can't do that. Your server crashes, right? But with Kafka, because you only fetch as many messages as the next part in the system, which is your MySQL connection, can write, you're safe. So that's what you can do with it. I think it's a really great piece of software. It's no longer it's still version 0.9 or 0.10 point something now, but it's very production ready. It has SSL support finally, and a few other clever things. So give it a shot. It's not easy to set up, so ideally to use some predefined Docker image or something, because it's not just Kafka, all the individual processes, then you need a system called Zookeeper for coordination. They borrowed that from the Hadoop ecosystem, so it's a little bit difficult to manage one of those clusters, but the nice thing is it scales from 10 kilobytes per day to 100 terabytes with 10 trillion messages per day seamlessly, right? So you set it up once, and then you can slowly start adding capacity just more nodes that can handle more topics with more partitions over time, and your code never has to change. So you have a little bit of an investment up front for a little bit of infrastructure. You need at least 3 nodes, so you have fault tolerance, right? You should ideally, if you run in the cloud, run at least in 3 different availability zones, because Kafka has this guarantee that it can, for n nodes, it can still be up with n-1 nodes alive. And so that's a little bit of work up front, but then even from your small use case now to the big use case in the future, it'll still work and won't let you down. So that's the end. Thank you. If you have questions, you can send me an email, ask on Twitter, or use the next 1 minute and 43 seconds. And if somebody gives you a microphone.